Okay, this is Miss Robertson, and we're going to solve some trig equations. But this time we are going to have something with the theta here, an omega or a phi, some sort of manipulation to our angle. When we do this, we're going to start the same way. We are going to isolate our trig function just like we did with the simple trig equation. So we want to get that all by itself. And so we need to get rid of this square root of 2. So we're going to divide both sides by square root of 2. And so what we end up with is this cancels out, and we have cosine of 2 theta equals 1 over the square root of 2. We won't find 1 over square root of 2 on our unit circle because the radical's in the denominator. So if you want to rationalize that, it will be easier to see. So cosine of 2 theta equals square root of 2 over 2. Okay, so just like before, I want you to ignore this. Pretend that this just says cosine of theta equals square root of 2 over 2. And so this whole thing is the angle on the unit circle. So we are looking for what angle on unit circle will give us square root of 2 over 2 when we take the cosine of that angle. So go to your unit circle, and we're looking for positive x coordinate of square root of 2 over 2, and there it is, right there and right there. So the angle is pi over 4 and 7 pi over 4. So we can say that this whole thing right here, this 2 theta, equals pi over 4, and the whole thing, 2 theta, equals 7 pi over 4. Now, the 2 tells us that we have taken the period of our original cosine curve and we have shrunk it by a half, which means that 2 complete cycles of cosine will happen. So here, let's just make this up. So here's cosine, okay, and so this right here is 2 pi. And so this is pi, and if we draw some line here representing square root of 2 over 2, we should have 1, 2, 3, 4 solutions. So notice right here we only have 2. To find the other ones, let's use general form. So notice we took whatever was here and we brought it down. We set it equal to our first solution and then to our second solution. And then let's add 2k pi to both of them. The original question asks us to find all our solutions between, so we want to look for thetas between 0 and 2 pi. So down here, we are going to use this formula to help us find those, but we don't want 2 theta. We want to isolate that and get it just down to theta. So we're going to divide everything by 2. So we end up with theta equals, dividing by 2 is the same thing as multiplying by its reciprocal, so multiplying by 1/2. So this is pi over 8 plus k pi. And over here, let's do the same thing. We're going to divide by 2. And so theta equals 7 pi over 8 plus k pi. Okay, so let's find the first solution. And how do we do that? We plug in 0 here. So when we plug in 0 here, we get theta equals pi over 8 plus 0 pi, which just equals pi over 8. And then when we come over here, we get 7 pi over 8 plus 0 pi, which just equals 7 pi over 8. Now let's keep going. Let's do this one again, but this time, instead of plugging in 0 here, let's plug in 1, so we get 1 pi. So 1 pi plus 1/8 pi gives us 9 pi over 8. Because this is 8 over 8 plus 1 over 8 gives us 9 over 8 pi. So let's do the same thing over here. 7 pi over 8 plus 8 pi over 8, if you want to look at it that way, equals 15 pi over 8. Now 15 divided by 8 is still less than 2 pi. But if we go much higher, because 16 over 8 is 2 pi, we're going to be too big. So our solution is pi over 8, 9 pi over 8. Oh, hold on. You want to do them in order. 7 pi over 8, 9 pi over 8, and 15 pi over 8. So those are all the values that theta can be. Now I want you to notice something. This 2 tells us how many times we're going to go around the unit circle, or how many times our original solutions will be our final solution. So originally we had 2 solutions. We multiply that by 2 and we have 4 solutions. So that number in front tells you a lot.